So
Good afternoon. So last class we stopped at how to interpret the linear regression result. As I mentioned, this is actually one of the very important application. So far, we try to tell linear regression with a focus to say how to do prediction, right? So you build a model, then how to predict a future observation. But there's certain category of application, they are more focused to say, what are those features relevant, right? As I mentioned, if you go to test, do a diagnosis for some health problem, then probably you take multiple tests. Each test will cost some time and money cost, right? So how to tell which are the more dominant features? Then linear regression actually provide a very simple and neat way to analyze what are those features kind of more contribute towards your final result. All right. So for example, if we look at our familiar linear regression function, we will say A1, A2. If A1 is much larger than A2, a very natural reaction to say X1 probably will be more important than X2. Why? Very simple, right? Any small change in X1 will cause a huge change in Y2. In Y, right? So that means if you say, I want to predict my, let's say, some health problem, I want to predict that by doing blood test, doing another X-ray, then I find actually my blood test result contribute more towards my final prediction. Obviously, you should do blood test or more focus on blood test result, right? That makes very simple sense. That is quite obvious. But there's one condition here. You need to normalize the different feature measure to the similar unit. For example, if you're doing one measure in terms of tens of thousands of units, but another measure in terms of 0.03 or 0.5, super tiny result. Obviously, you will expect your A usually will be a little bit small, right? Your A2 will be usually in a much larger quantity. So that doesn't to do the fair business. So what we do is we need to normalize all the features to make sure they are measured in a more or less comparable range. So I hope that makes sense to you. So to, for example, make everything look more or less comparable. So then your weight, your linear weight, A1, A2 will start to give more meaningful indications. All right. So how to do the normalization? So actually pretty much I was talking, was covered in these slides. So basically, if I fit a linear regression model and get something like this, does this mean X2 has a bigger impact than X1? Because X2 associated with 100, X1 with 10, usually can, but not necessary for now if I didn't specify they are normalized. All right. So not necessary because we haven't said anything about the range of X1 and X2 that result in A1. So this is very tricky, pay attention. So we need to, when you be asked whether those linear weights indicate the importance of different features, you need to first check, is there any condition to say they have been normalized? If not, then the answer is not necessary. If indicate, of course, you can. So one solution is normalize the data before doing linear regression, so the coefficients are comparable over a consistent range. So how to do the normalization? One way, at least this is one very popular way, is to do standard normalization. This is a very similar. This will remind you how do you calculate your z-score. So what to do for each column? So remember, our feature matrix contains each row is what is a particular measure particular observation or samples. Like in our example, one row corresponding to each student, for example. Then each column denotes a particular feature, right? I measure how many hours you have studied. So the column contains all the number of hours, study hours across all the students. So now we will take that column. All right. Take that column and normalize it. So what we want to do, our objective here is try to make each column to have a zero mean and standard deviation of 1. So this, I hope this reminds you the z-score calculation, right? So how to achieve zero mean? Very simple. Subtract the column average from each feature sample. Right? If you take away, because if you calculate the average, now if I take away the average from every single one, of course you get a zero mean, right? That is very simple calculation, right? So this was useful to eliminate the bias contained in the feature. Okay. And another one is try to scale those values. Try to divide each feature sample by the column standard deviation. By doing that, you achieve standard deviation of 1, right? So basically in the first stage, you try to center your measure to make them centered at 0. The second one is try to scale them a little bit to make them with 1 standard deviation. All right. So mathematically, it's very simple. You just try to do something like a z-score. You take away the average, then divide by the standard deviation. So this is the target to apply this is each column. Okay. So we are talking about the column in your feature matrix. Okay. Does that make sense? Any questions about this standard normalization? Is it very straightforward? Yes. Question. Do you use the population standard deviation or just like the sample standard deviation? Oh, this is a sample standard deviation. You calculate from your column, right? If you have this column, you can calculate the standard deviation, right? So, all right. This is a one of the very typical way to do normalization. Of course, this is not the only way, but this is probably the way, the one which we introduced during this class. So for example, I can give you a very simple, another very popular normalization, which just nice to know. I don't require you to memorize those. Yeah. So another way, for example, I try to normalize all the values in each column to between 0 and 1. So how to do that? Think about that. Actually, this is a very good exercise to think about that. Yeah. Take maybe 10 seconds to think about it. If I ask you to normalize each column to between 0 to 1, how do you do that? Very simple mathematical calculation. Okay, so basically let's say let's denote this column as a small x as a vector. Okay, so what you can do is you can try to find what is a minimal in this vector. Right? You just scan through what is a minimal value inside, right? And then you try to find what is a max value. inside. Okay, so then what you can do is then you can go through this vector, take each of the particular value, just like xm here. Then you take away the minimal. Then divide by x max minus x min. So you can see that now you actually put your value in a particular range. Does that make sense? Right. So this is usually they will give more or less very similar performance, but sometimes we don't know in advance. So when we treat different problems, you might try it with different normalization to see which one give you the best. But of course, in this class, only the standard normalization is required to be understood. Okay. All right. No, any questions here? So once okay. So this is talking about how good is a fit. We know how to get a linear regression coefficients, but then we need to tell how good is your model, right? One obvious measure we have seen so far is the mean square error. Right? Those epsilon. Remember, we fitting a line, and then each of the y, they still have a small deviation from your model. That is an epsilon, right? Each point will contribute a small epsilon. If you take a square of them, then sum them all, this will become your square error. Okay, that is one measure. But here we want to introduce another one, which we call R square, which is called coefficient of determination. So this R square, the formula to calculate R square is this. Okay, so here a few notations. This y hat, yn hat is what? Is the model produced value. Okay, because for each point, you plug in your x in your line, you will get a y hat, which is a point on your line, right? So I think I mentioned this before. You have a lot of points, then you fit a line. So this guy will be your yn, and this guy will be your y hat a. So because y hat n is what your model, because your model can only produce points on the line. So this will be, this small deviation will be yn minus y hat. Okay. So the y bar here, y bar is the average over all ya, is basically the average. Okay. So as you can see here, the upper part, this is your mean square error, right? So this is exactly your mean square error. And then the bottom part is what? Is your variance, right? How do we calculate the variance in y? You calculate the difference between each y with their average, then take square, then sum them all. This is exactly the variance calculation, right? This, I hope you see that. So this is a, so basically R square is 1 minus mean square divided by your variance in y. So now I'll try to take a look why this R square can give you some meaningful measure. Let's think about that. Yeah, so first of all, what is probably what is the range for R square? This is first question to think. And then if R0 equal to 0, what does that mean? If R0 equal to 1, what does that mean? Think about that. And I will enter the more, I give you more details next, but try to think about that. If R square equal to 1, Does that indicate anything, or R square indicate 0? What does that mean? Okay, so I think I will try to provide more details about why this R square measure is a good measure. So let's look at this figure. This picture actually tells the story. Those cross sign, those things are your observation, right? So this is what you observed. So now you try to come out with a model. The model in our scenario will be this linear model. So basically, in this case, we are looking for a line. Okay. So if we are very lazy, we don't do any fitting. We just say, let's be lazy and just try to take the average of your y as a prediction. So no matter what you give me, I just always give you the average of y, right? That is not too bad. I mean, at least it's not like unreasonable guess, right? But this is a lazy version. So you tell me anything, I just give you. You tell me how many hours you study. I just tell you. Okay. My predictions, you will get the, like, for example, 75, the average of the exam one. I mean, a good guess. Okay. But it's a lazy one. Okay. So if I can give you exactly what your observation, then that is ground truth. That is perfect, right? Then in the middle is what the model will tell you. All right, so now you can see what is so basically now what we try to measure is to measure the proportion of these two, because this part is unexplained by your model. It's like the epsilon. Okay, so this one is the explained variation, and then the whole thing is your variance, right? Do you see that? So now you are trying to measure how much is this portion over the whole range. So this will become your second part, the MSE divided by your variance. Then you use, of course, using 1 minus this by some design, which was swap 0 or 1. You think 0 is good or 1 is good. Yeah. So by this, now you will see if you have R squared equal to 0, that will be very bad. That means R squared equal to 0. That means this guy will equal to 1, right? So basically the MSE divided by everything will equal to 1. That means I have the lazy version. I'm stuck with this line. You can see I didn't explain anything. I just, every time you give me a number, I will tell you the average. So if the R squared equal to 1, that means this guy equal to 0. So that means this part, this MSE part is equal to 0. So that means my line always explain your observation. Do you see that? Okay. I hope you now you see why this is a measure makes sense. Yeah. So MSE is good enough, but sometimes because this one is taking into account of MSE, but also the variance of your target value, right? So this is a more comprehensive measure. So sometimes we like to have R square. At least the R square is a very common measure. Okay. Does this make sense? Any questions about this R square? If you have any questions, go back to look at this picture and think about the lazy version. So you don't train anything, and if you ask me anything, I just give you the average. That is the worst I can do. that will give you a 0, because now the MSE is equivalent to your values. All right. Are we fine with this? All right. So now we are talking about how to put things together. So basically, this is a more overall picture how things will be integrated. So basically, after you fit a linear regression model, you can estimate or predict the target Y of new points, data points. I think that we have talked about this, and also we have seen examples. At the end of last week, last class, we end with an example, right? So you can see we have 5 points. If you remember, we have 5 points. We are building a model. Then I ask you what is a -1 and 1, a new point. What will be the prediction value for that? And then we just try to calculate from the 5 points what it will be those A1, A2, and B, and then we plug in the X1, X2 of the new observation. Then we will get a Y that will be your prediction. So this is essentially how to generate new predictions. Okay. Then you can say how good is prediction. You can try to do mean square, or you try to or R square. So of course here, yeah. So here I want you to know this is means sometimes I think actually we will talk about this part. Yeah. Sometimes if you want to assess how good is your model, you need to hold a small portion of the data which has the answer, right? Because to assess either the quality, you need both have your prediction and Y. You need to know what is the true Y, what is your predicted Y. So unless you have these two, there's no way to assess how good you have done, right? So you need both of them. I think that you will see more clear about the picture about this part, how to validate, how to test your model. So we will come to that part. But so far, I think that it's good to know we are able to assess the quality of model by using, let's say, mean square error, using R square. And if we want to do some analysis, want to interpret the model, the normalization is also important. Okay. There's one thing I want to point out in this picture. We normalize both the input feature and also the target value. In my understanding, this part can be optional, right? So sometimes we try to normalize. We typically normalize the features, and try to normalize the Y can be optional. But if you choose to normalize your Y, you remember you need to denormalize your Y after you output it from your model. I hope that makes sense to you. Okay. All right. Any question about this slide? So to implement a linear regression in Python can be super simple. Yeah. So in this class, we will try to introduce or recommend you to use this sklearn. Sklearn is contains a lot of useful stuff, a lot of classifier, a lot of things inside. Yeah. So and also of course you import necessary functions or modules, and then try to follow this outline. This outline is applicable for quite a category of the method in sklearn. So basically, first you try to create an object, create a linear regression object. So this is an object which is probably don't see any data yet. It's just a preparation stage. Or there's a one parameter called fit intercept equal to true. So that means you want to have B. Okay. As I mentioned, when you have AX plus B, the B will allow you to move up, down of your linear model. So will make your model much more powerful. All right. So after you create this regression model, then you try to call this. This is a stage to input your data. As you can see now, we call say regression.fit x train, x y train. So this is your training feature. This is your training label, right? You see that, right? This is a x and y. So now you give the regression model the data you have. You say, hey, go ahead to fit those data. Then after the fitting, so this is actual training stage. So after this stage, the model already found those are A and B, those weights. All right. So after this stage, you can call regression coefficients. This will give you A1, A2, AM, those A's. And then the intercept, this will give you the B's, right? Once you have all the A's and then the B's, the B, you have only one B, okay. So you have all A's and then that only single B. After you have that, you will have your regression model. All right. And now, yes, question. Yeah, because you don't need to have B. You can try to find a line, go through the origin to fit your data, right? Because if I give you a lot of points, you can always find a line goes through the origins, right? So this does not only allow you to rotate your line. Sorry? I believe so. So I'm not 100% sure. But usually we most often will try to use the B. But later you will find in a more complicated scenarios, sometimes if you do not even have B, that's fine. When we do, for example, the deep learning, sometimes we typically have B, but then the B will not be as sensitive as here. Yeah, usually we will write X plus B, but I want to show you the B can be 0. Who knows? For some applications, the B equal to 0 will make your solution better. So after we have this regression model be trained, then we can start to enjoy this model by generating predictions for unseen data, right? So now you just need features. You do not, now you do, during this stage, you do not need Y. You just tell me what X you have, right? What features you have. And then this regression will try to predict. The predict is very simple. It's although this is very fancy to say predict, but actually we know this is just doing A1 multiply X1 plus A2 multiply X2 plus B, right? So doing this, yes, question. Oh yeah, this should, in this case, I think that we will consider this as a matrix. Yeah. And sorry, yeah, so you will get y predict, all right? As you can, as I mentioned before, in order to assess how good is your model, to basically to compute, let's say R square score or compute the MSAE score, you need to not only have this y predict, you also need to know what is the ground truth of those y. All right. This is a. I hope this is this looks reasonable to you. In order to assess how good is your prediction, you need to compare with what is the actual ground truth of those y. If you do not have those y, it's difficult to assess whether you make the right prediction, right? So this is a evaluation stage. You need both the ground truth and of your prediction. Then you see how off are they. Any questions about this the Python code stage? We should see more examples, I'm sure, for this. Yeah. But so far, any questions about how to write a linear regression using sklearn? Yes. One more time. Yeah.
So you know how with NumPy we say import NumPy and
Oh yeah. Well, probably this is just it's not complete. This is just a piece of code try to highlight the sklearn stage. Yeah, I'm sure you. Of course, you here you need to prepare your X train first, then prepare your Y train. You need to load them into the corresponding matrix, right? So you need to load the data, the input there. Yeah. So for those stage, we just skip for now.
And when you do that as NP, NP is just an alias for NumPy.
yeah.
So Python sees NP and interprets it as NumPy. For sklearn, there's no like standard abbreviation for it. For NumPy, it's just standard to abbreviate NP.
Okay, thanks. Yeah. All right. So we are talking about say, hey, let's prepare our feature by normalize them, and then we will say, so using this, we can roughly see their magnitude to indicate which feature are more important. But now if I ask you another question, so does one particular feature actually is useful to be included or not, right? It's significant. It's not necessary to be all significant because at the beginning we design our data collection probably just based on imaginations, right? We think, hey, this probably your exam result will depend on how many hours you study, how many hours you sleep. So probably it doesn't. Who knows? So we need to find out, right? To do this, and we can rely on our friend of hypothesis test. Very simple. We can just create, just like what we did before for our exam one, to say you create a non-hypothesis to say one particular coefficient is 0. That means that feature has no effect to our final target value. Okay, and then the alternative hypothesis is say, of course, the coefficient is not 0. That feature has some effect. I hope this makes sense to you. Right? It's because you list in our example, I talk about two features, but a lot of time you probably end up with 1,000 features, 2,000 features. You don't want to use them all. You want to make your model simple. Try to find what are the most critical features, right? So then this becomes very important. Try to say, which are the features I can throw away? I just find the dominant set of the features. And after you create this, the general philosophy is almost exactly the same as what we did before, but there's only tiny difference here. is how we calculate the standard error. Okay. Let's pretend we already know how to calculate our standard error. Then what you need to test is simple, right? Is just using this what you actually have divided by standard error, right? Because you want to take away the a, but because the a you assume is 0 in your non-hypothesis, so you end up with test this guy to take your actual a divided by a standard error. Right? I hope this remind you how you calculate the z-score, right? So now the only difference part probably you need to remember is how to calculate the standard error is using this. Okay, so there's two parts. For the denominator, you try to calculate the average of that feature column. So now the x, so you see the xm, m is a feature index. Think about you have a x matrix, right? I was talking about each row is a particular student. Then each column is your number of study hours, number of your sleep hours, right? So now I'm taking, let's say, the first column. I will say how this will be your average study hours, will be the average of the first, let's say, the first one particular column, the mth column. Then this is basically calculated the variance for that particular feature column. Any question about the denominator here? And the numerator is, you can think about this as a, is a type of variance, right? Sorry, is actually this is a n minus 2. This n minus 2 is some kind of degree of freedom. If you recall when we calculate our, if you still remember, we have the t-stat statistic, right? We have one parameter called degree of freedom. Yeah. So just remember those formulas. I think that for now, you just think about we using some stat to calculate some statistic. Okay. So this is your this is your ground truth yn, and then this y hat is your predicted value, and then this is your feature value, this is your feature average. Then plugging all the data you have in this way, you will get your standard error. Okay. And then with this standard error, you are able to calculate some kind of this score like of value, then to calculate, to plug in into your hypothesis test. All right. Are we fine with the concept here? Any questions about this? You're able to just try to plug in this into your familiar hypothesis test and see. The only difference here, I would say, is how this particular way to calculate the standard error. And other than that, I think just repeat the same story. Are we fine? So now so far we are talking about linear regression, but we give you a fake impression we only fitting lines, but that is actually not true. When we talk about linear regression, the coefficients, they are linear, but the feature space not necessarily to be linear. So I will explain what does that mean. Okay. So sometimes we do want our linear regression to produce some kind of nonlinear relationship, represents to match to some nonlinear data. For example, for this data looks like a line looks fine. This one, a line looks fine. But for this guy, obviously a line doesn't serve the justice to the data, right? So probably if you make your model to be a little bit curvy, you fit your data perfectly, right? You see that, right? So basically, let's say the relationship between the y and x is different in each case. So, and possibly we try some nonlinear mode. Okay. A common misconception is that linear regression can only find linear relationship. So as I mentioned, that is not true. The linear part will refer to the parameter vector beta, but not in the features in the feature matrix A. All right. So for example, you still feel mysterious, but take a look at this line, this equation. This is a perfect linear model in terms of parameters. We have A1, A2, B, right? But what's the trick we play here is we are bring our feature into a quadratic format. You see that? So now instead of we are considered about x, we are considered about x squared. So basically you are trying to fit a linear regression model. So still is a linear model to a nonlinear data. Okay. So to achieve this, we will modify. The only thing you need to modify is to make your feature matrix to contain some of the high degree. We consider about the quadratic here. Of course, you can raise the power, you can consider the cube, right? You can, or even raise the power to 4, raise to power to 5. You can create as fancy from the non-linear space as needed, but at the cost of whenever you bring some additional high degree terms, one thing is you are adding more parameters. Okay. The second question is, will you fit your data too much? So that is one question we will talk about in the next slides. All right. Remember, if you have a quadratic, you are doing something like this. Still is a pretty nice curve. But once you are going to high degree, let's say you have a square raised to square 510 plus, like you have A1, A2, X3. Yeah, if you have this kind of complicated terms, what is curve looks like? Your curve probably can be a very arbitrary some kind of curve, right? Because it will fit a lot of very fine the small details inside your data, which is not necessarily the good thing. I will talk about this in these slides. So for example, if we take to make your highest term to be 0, that means you only have a constant, right? Because you are fitting a constant line, so you will get something like this. You have a constant line. If you have degree 1, this is the one which we look at so far. You are fitting a line. Okay. If you have degree of 2, you are kind of fitting this kind of quadratic a curve, which is pretty beautiful. If you have degree 4, in this case, it's fine. If you have degree equal to 8, then you can see you start to fit those, how say, those very fine details of this inside your training data, right? A lot of these small bump up and down, you start to capture them. When you have a degree equal to 16, this is probably you are fitting this even to some to handle a lot of extreme details. Remember our basic 2 metrics to say a model is good or bad. The first is what? Explain your observation, right? Your model need to explain the observation. Then what is the second? Second is say to explain those unseen data, to generalize to unseen data. So you need to explain, you need to generalize a bit, right? So when you have, just imagine you have this type of fitting these small details. This can be difficult to generalize to future, right? Because you are fitting, you are way fit too well to your particular observations. So I doubt in future observations, you are training some kind of model like this. If you say future models training something like this, is more likely to happen. You have because it's pretty simple, pretty genetic. This one is also okay, but for this guy and this guy, although it will fit your observation, current observation very well, I suspect it will not generalize well. Okay, so this is so we always need to find a trade-off between the how good is your MSE, and then another thing is you need another regularization to avoid you explain your current observation too well. I think that in the next class, I will talk about some strategy to how to punish those models which create this type of overfit. Yeah, so have a nice weekend.